Right. So today I want to talk about the quantum version of what we've been talking about for the last couple of lectures, which is Noether's theorem. And I'm going to show you that while Noether's theorem is a strictly classical statement, there is a quantum version. And that quantum version, in the same way that Noether's theorem kind of constrains the solutions of a particular theory, the quantum version of Noether's theorem is something called Watt identities. They give you constraints of the correlation function of the theory. Okay, so because it's a quantum theory, there's no, path and phase space that we talk about. We talk about correlations in the theory. So anything that we say about theory has to be framed in the language of these correlation functions. And on the way to showing you what the quantum version of Noether's theorem looks like, we're going to have to talk about what the quantum version of the Euler-Lagrange equation is. The quantum version of the Euler-Lagrange equations are set of equations that govern correlation functions in the theory. These are called Schwinger-Dyson. Okay. All right. So at this point, I'm going to assume that everybody at least perused my notes on the path integral. We don't have to compute arbitrary path integrals. At the point, I just wanted to have gleaned enough from the notes to at least have some familiarity with the symbols involved. Okay. So I'm not going to talk in any detail about the path integral. What I am going to do is to use the ideas of the path integral to frame the economics. All right. So I want to start by just reviewing what the equation of motion, look like in a quantum system. And we're going to be working entirely with the obviously operator versions of what we're talking about. You might see this in Will Horowiz's not the very close, I'm sure. But we're going to be sticking with the functional formulation of the path integral formulation structure. Right. So before we go there, I want you to recall from first year that if I have some function f of x and I want to compute the average of that function over some volume, in this case, some interval in the real line, then what I do is I take the function and I integrate it from a to b, and then I divide by the length of the interval b minus a. And this defines for me the average of that function over that interval. Right. What's important here? What's important in the story is this quantity here, which is the volume of the interval from a to b. I like the word volume here because it's generalized to high dimensions as well. It's the fact that the quantity that I'm trying to average is sitting inside that integral. So the average quantity and then I'm integrating it with respect to something. It's the measure of the integral. Okay. And statisticians, unlike mathematicians, call this the average of the function. That's the average. That's how you calculate it. So, what we want to do, all we're trying to do is calculate these averages. These are the difference between that and this, and that we're calculating quantum averages. And this is what the path integral does. So, I'm going to start by just illustrating something with what's called a 2-point function or 2-point correlation. So given two fields, or given a field phi, what I want to do, calculate this 2-point function, is calculate the quantum average of this product, phi at x1 and phi at x2, 2 points. Okay, so I evaluate phi at 1 point x1, another point x2, multiply those two together, and take the average of it. And that average in this case signifies, is technically defined as follows. I pick some state in the Hilbert space, say omega, and I sandwich between the state omega, phi at x1, phi at x2. And this is called the time ordering operator. The story here is that there's some ambiguity in how these operators act on each state. And the ambiguity stems from the fact that these things are non-commuting operators in the Hilbert space. So I need to be clear about the convention that I'm using when I order these operators and their action on the state. Right? So basically, what I do is I take the state here, any state you want, some fixed reference state, more often than not. This is taken to be the vacuum, right? So this is some reference state in the Hilbert space. For example, the vacuum state. And then I act with these guys on this state in the following order. This is by convention, right? There are other correlation functions that I consider that don't have this convention. One in particular that's quite popular these days is the convention of chaos, the other time order correlation function. But basically, what I do is the following. This time order operator ensures that these guys here are x mu and x mu, right? X mu1 and x mu2. They have a time and they have some spatial points. What it makes sure is that if this guy occurs earlier than this guy, then this guy acts first on this day. If this guy occurs earlier than this guy, then the time ordering operator flips him around, so that the earlier operator acts to the right first. That's what it does. One of the neat things about the functional formulas is that we don't care. It takes care of this automatically for us. And I put this in my notes. You're welcome to go see the proof. But essentially, this is one of the benefits of the functional formulas, that everything inside the part integral you can treat as a classical game. Right? So this 2-point function, that guy there, is 1 over there times the integral over all fields phi of x. Phi x1, phi x2, e to the minus, e to the I s of phi. Okay, so let me unpack this. So the first thing you can see is that the structure of this 2-point function is very similar to this. Okay, so these angular brackets here indicate that we're taking a quantum average. And then quantum average is defined as this operator here. Okay, I start off with a fixed state, act with phi, then project up to this state. That's how we define the quantum average, right? But I can give a functional integral version of that quantum average by writing it out like this. This guy here, the denominator, is the normalization function, which is basically just that. And you can think of it as the volume of the subset of the space that we're working with. Right? So again, it plays the role of 1 over b minus a, which in that context as well normalizes the average speed. Okay. And this is these two things together. Okay. This is the integral measure weighted by the classical action. Okay. So there's a long scale about all of these things in my notes, and I again encourage you to go there in detail. The point is that if I want to calculate a quantum average of this, for example, 2-point function that involves a product of two fields evaluated at different points, then this is how I calculate. Okay, take those two fields, stick them in here, and notice in here there's no time ordering operator or anything like that. That's because inside the integral, I think there's classical fields. Classical fields don't have any ambiguity associated. Okay. And then it's weighted by the classical action. So the classical action. Also. This is important. Okay. So to build some intuition for what we're trying to do, namely to get the quantum equation of the motion out of this, I want to pick a specific technical action, just so that we have something to work with, and I'll write down the general version of it once we're done. So just by way of a concrete example, let's choose so let's consider the three massive scalar whose action S X is a half, and let's say we go to 4 dimensions again for completeness. So this is a half dv of phi squared, which you understand I mean dv by dv phi, minus a half m squared phi squared. And just to remind ourselves, the classical equation of the motion follows from this action. Once you go through all the rigmarole of doing it, the Euler-Lagrange equations, but strictly what you're doing is you're demanding that action be stationary under some transformation. Right. So classical equations of motion corresponds to demanding that delta S equals 0 under transformation variation. That's phi of x to phi prime of x, and phi prime of x is phi plus some small epsilon of x. Or you might call it delta phi, but this is called epsilon because it's going to need it in one follows. Okay, so this is how you calculated the task equation of the model in the field here. So basically, what you would do is you would take this change in phi, you would stick it into here, okay, and then you would isolate all dependence on epsilon, pull it out of the square bracket, And then you take the functional derivative of this with respect to epsilon, set it equal to 0. That's what it means for this to be stationary. And what's sitting in the brackets has the value of any epsilon, and that would be the Euler equation. Okay. As far as the functional integral is concerned, though, this variation, and then we call the variation the classical theory, is nothing but an infinitesimal change of variables. Moreover, it's an infinitesimal change of variables that leaves the measure of the integral unchanged. So at the quantum level, Q is infinitesimal. Change of variables. Leaves the integral measure d phi of x equal to phi prime. So what this means is that if I calculate the 2-point function, then phi integral d phi of x, phi of x1, phi of x2 equal to d phi s of phi is equal to the integral d phi prime of x, phi prime of x1, phi prime of x2 e to the I s of phi prime. Now we do what we would have done in the classical story, which is to expand the action in phi prime, keep terms to linear order in epsilon, right? And then see what we need to get set equal to 0. So I'm going to expand this right hand side to linear order in epsilon. Again, the details are in my notes. But essentially what I'm doing is a Taylor expansion of the right hand side by substituting phi prime equal to phi plus epsilon. I'll get the integral d phi of x e to the is of phi times factor of I times integral d4 x coming from the action epsilon of x times then that looks like minus box minus n squared acting on phi of x multiplying phi of x1 phi of x2. So this term here comes from an integration, this box comes from an integration by parts of this term here. So this is the du by part once. I get a du part. That du is slightly the version. The minus sign comes from integrated by parts. The factor of half comes from the factor of half here is capital R minus factor of 2, and then this factor of half capital R minus factor of 2 comes from taking the derivative. Plus a term that looks like epsilon of x1 phi of x2 plus epsilon of x2 phi of x1. This is to leading order epsilon. Okay. And I need this leading order term in epsilon to vanish. That's what it means to be to demand that delta S by delta epsilon vanishes in classical equation, right? So there's some piece that doesn't involve any epsilon, that piece will match up to this guy. Then I take the difference, and that'll be 0. And then there's some piece that will be epsilon, and there's some piece that will have higher order terms than epsilon. We're assuming that epsilon is an infinitesimal change. So any higher order terms are cancelled. So the only term that really matters is the term that's linear in epsilon, and that's this one here. And now I need to put it in a form that will allow me to read off the epsilon dependence. The problem here is that I have epsilon evaluated at x1 and epsilon evaluated at x2. Okay. So one thing I can do to get rid of this is to write so I can use the fact that the Dirac delta distribution is a sampling function. So I can write this guy, epsilon of x1, I can write it as the integral over dimensions, epsilon of x, delta of x minus 1. If I integrate, if I multiply the Dirac delta function against this epsilon of x integrated over all space, it will sample this function at x1. So that is x1. Similarly for x2, I can calculate it the same way. So basically what I'm saying is either I equals 1, 2. And if I do that, and I demand that this variation vanish for any epsilon, then I can pull out an epsilon from here, I can pull out an epsilon from here, and pull out an epsilon x from here. Demand that that variation vanish for any epsilon, and this means that the integral d phi of x e to the is of phi box plus m squared phi of x phi of 1 phi of x2 plus I delta of x minus x1 phi of x2 plus phi of x1 plus I phi of x1 plus phi of x1 times I delta of x minus x2 equals 0.
People have the Derivation equations.
No, I've taken out the 4x integral outside of all of this, and there's an epsilon sitting outside of all of this as well. And I demand that what's left inside the brackets must vanish. Okay, so that's why I'm using the d4x here, d4x here, d4x here. Take all that out of the factor of pi, which accounts for the minus signs here. Right? Exchange the order of integration. What's sitting inside is just the functional integral with the sum of variables. So the point I'd like to make here is that even though I chose to focus on the 2-point function as an example, there's no reason to consider the 2.5, right? To know for any 0.5. So if I calculate the average for example, 1.5, which is the single pi, then similar relationship involved as well. And you can start to see the structure here. The first term has pi, pi, pi. These two guys come from 2-point function. This is coming from the action. This guy has the original 2-point function that I wanted 5x1, 5x2, except I replaced the 5x1 with an I delta, and I replaced the 5x2 with an I delta. Yeah. Okay. So similarly, for a 1-point function, we would expect that the integral over 5x e to the is fine. Right, e to the is of 5 of x, 5x1 plus the integral t phi of x e to the is of 5 times I delta x. Notice that these two terms didn't have any 5 x's. Okay. Well, this guy here doesn't involve any 5x, right? And this integral is telling you to take the integral over all fields of 5x, but there aren't any fields 5x here, so this is independent of this. So this here is just slightly what I was calling integral partition function of the Euclidean set z. So now if I divide 3 by z, rearrange the list, I will find. Oh, sorry. I'm seeing a factor here. That factor is box plus m squared by x by x. Now, if I divide 3 by z and rearrange this a little bit, I will find that box plus m squared integral d4 phi of x no, sorry. Box plus m squared don't involve any phi's. So again, I can take it out of the integral. Integral d phi of x e to the is of phi of x phi of x1 equal to minus z I delta of x minus to power. And now if I define my quantum average normalized by z, and I divide through by z, if I divide both sides by z, then the thing on the left hand side is just the 2-point function, normalized 2-point. And the thing on the right hand side is minus pi delta x minus x1. So let's stop and take focus of what we've done. What have we shown? We have shown that this 2-point function, right, as long as x1 is not equal to x, this 2-point function satisfies the classical equation of motion. Classical equation of motion associated to this action here is simply box plus m squared phi of x equals 0. That's a fine logic, right? Okay, so the classical equation of motion that I would have thought, if I just thought about this as the classical theory for the speed of phi, is that the derivation plus m squared phi of x equals 0. Then I would go ahead and solve it with some boundary condition and alter. What have we found? Well, we found that when we go to the quantum system, okay, so now we speak about quantum. So yeah, principally you should have hats on this thing. That the correlation function, as long as x1 is not equal to x2, and this side is 0, the correlation function satisfies the classical triangle equation. Okay, the thing that makes this thing quantum is precisely this non-vanishing right-hand side. This is what's known as a contact term. Now, the contact term arises from the action of the derivatives in this box operator on the time variable and the fact that I'm taking a time ordering on this thing. So actually, in principle, I should write the time ordering product. So there's an ambiguity in how the time derivatives in the derivation operator act with respect to this time ordering operator. That's where this contact term comes. And the contact term is precisely what makes this thing quantum. And the fact that we can only talk about this operator acting on the quantum average of this 2 parameters. Okay, so statement is that one, the as long as x1 is not equal to x, the correlator satisfies classical equation. Okay. Two, the right hand side of equation 4 is called contact term. Because it really only comes into play when x is equal to x1. That's this. The T naught squared derivatives thing. On then finally, 3. That equation 4 is the quantum analog of the classical quantum number equations. It is what we call the Schwinger-Dyson equation. And what we did here was really specific to the free math of scalar. You might wonder what it would look like generally. So more generally, that's not cool. More generally, if I consider some field phi with dynamics governed by some project, let's say L phi, and we imitate what we did. If phi of x has a project density L of phi of x, then the Schwinger-Dyson equation reads L by phi minus mu L by g mu phi on phi x1 to phi n average, which will be about the path integral, is the sum over, let's say, line equals 1 n of phi x1 all the way through to the k phi, where I replace the k phi with in fact it's a k for 1 where I replace the k phi with x minus x k. That continues all the way to phi n or the n point. It's general universal. So the point here is that I write out this endpoint function as a sum over recursively n minus 1 point functions. Right, and I keep going. So you may have seen an expression, the Schwinger-Dyson equation in terms of Feynman diagrams. This is the full endpoint function you want to calculate, and these are all sum functions calculated in the same way. So this is the general Schwinger-Dyson equation, and it is the quantum version of the classical equation of one. Right. So to finish off, I want to say now that we've understood how to go from the classical equations of motion to quantum equations, let's see if we can frame Moses' theorem, the classical statement, in this quantum language. Our strategy is going to be the same as what we did with the classical to subject where the action gives a functional integral to some infinitesimal changing variables along some symmetry direction, and then promote the parameter from a constant to a function, and see what we can do from there. So here again, I'm going to start off with an example, and the example I'm going to use is going to be one of a free complex scalar. So consider free complex scalar. If you remember our last example in the last lecture, the complex scalar was equivalent to a charge scalar. The fact that I had this phi star d phi minus phi d phi star term, right? And phi star, phi conjugate, not the same thing, means I had a charge associated with this. So this charge was a conserved quantity associated to the continuous global phase rotation. Okay. So consider the free complex scalar, whose Lagrangian density is mod d mu phi squared, where I mean d mu phi star minus m squared phi squared. Just by the way, you would notice that when I wrote down the Lagrangian density for a neutral scalar, there were these factors of half being in there. These factors of half get soaked up by the fact that there's actually two real scalars in a complex scalar. Okay. So that's why you won't get that out. So we already know that this theory is invariant, that there is only one phase rotation. This is invariant under a local U1 phase rotation. I remind you that U1 is the set of all objects that go back to the I theta. Theta goes from 0 to 5. So what we want to know is what are the quantum consequences of promoting the parameter, let's say alpha, right? Promoting this alpha, which is a constant there, to a function of x. So what happens if alpha now that's on the x in the quantum system? Right. So we want to make the infinitesimal phi of x to 5x plus I alpha of x 5. Okay, so we consider alpha very small and somewhere being equal for 5 star minus sign the I. The first thing to note is that this is a unitary transformation, which means that I can undo it by conjugation. And it also means that under this transformation, the integration measure is invariant. This is important. So this is a unitary transformation of fields. Leaves the integration measure invariant. And I'm going to use the notation here. It's strictly I do the same thing for the 5 star, because I'm thinking 5 star as an independent thing. So when I do the integral, I'm going to integral over 5, I'm going to integral over 5 star. this is I think so, I'm just gonna write one better. So what this means is that the path integral, well, let's say it's 2-point function. So integral d5. This has been integrated all fields. Phi e to the power s phi of x1 phi star of x2 is equal to the integral of d5 prime e to the I s of s of phi star s of prime phi prime. Phi prime of x1 phi star of phi prime star of x2. What I mean here is that I need to evaluate this thing at 1 plus I alpha times phi. Okay. That's my prospect. So I'm going to leave the details out here, partly because we're running out of workspace and partly because we're running out of time as well. Not running out of space, but we do the same thing. We expand to linear order in alpha. We integrate the term that will take a dmu alpha by parts, so we put the derivative across. And then I write instead of alpha xi, I write it in terms of this direct delta function. And then I pull out all the d4 x's. So the following, and then I divide it by z. So expanding to linear order in alpha of x, integrating parts. The alpha and writing alpha x I and that's equal x alpha x delta x is y and dividing by z. We get the following. We'll find that the expectation value of d mu j mu of x against phi x1 phi star of x2 equal to minus pi times the expectation value of I phi x1 delta x1 is x1 that x1 yeah. Phi x2 plus phi of x1 times minus I phi star of x2 delta x2. Okay. This is the Schwinger-Dyson equation associated to the current conservation. Okay, and you can see that as long as phi 1 and phi 2 are not, as long as x1 and x2 are not equal to 0, not equal to x, and x1 and x2 are not equal to each other, then this implies that d mu j mu equals 0. Okay, because it must hold for any one of these steps. But this is the quantum version of the current conservation statement that d mu j mu equals 0. Again, the difference between these two are the contact terms. The difference between the quantum and the classical version, contact terms on the right hand side of this expression. This expression then gives us a constraint on the correlation function. Any correlation function that we calculate must satisfy this. This j mu, by the way, is the usual one that we've described previously as I phi d mu phi star minus phi star d mu phi. Okay. And this constraint that we get on this correlation function is called the Ward identity, and it must be satisfied by any of these correlation functions, that it is the quantum version of the classical theorem. Those of you who are doing quantum field theory in particle physics, you will see a version of this. This is what some people would call the generalized Ward identity. You will see some version of this in the context of scattering problems, in particular, where it goes by the name of the Ward identity. Okay. But Ward identities are effectively the same thing as the Dyson equation, and they offer constraints that must be satisfied by the quantum correlation functions that are the equivalent state of the quantum system to classical theorem. All right. Okay.